basically the easiest algorithm in the CPU scheduling, among the CPU scheduling algorithms. Alright, so we have the process here, the burst time here, and the arrival time here, and we need to find out the Gantt chart of this, and we need to find out the waiting time for each processes, and then eventually find the average waiting time. Alright, so in this case the arrival time matters because we always serve that process whichever comes first, and we complete that process fully as it is. So the burst time for the first process is 5, and it's really big compared to 3. So your logic would be like, why not just execute 3? Because it's smaller, let's just get rid of the shortest job first, and then we can do the longer jobs. Well, we'll come across that in the shortest job first algorithm. So, but in case of FCFS, we just execute the processes that come as they arrive, like however long the processes, if they arrive first, they get the priority first. So let's draw the Gantt chart for this. Okay, so for P1, the burst time is from 0 to 5, so 5 seconds are executed. For P2, it's 4, so 5 plus 4, 9. For P3, it's 12, 9 plus 3, 12. And for P4, it's 12 plus 6, 18. Alright, so this is the Gantt chart that we produced after getting all this, after using all this information. It's really easy. You just apply this axis just contains the burst time, and these are the processes. So according to the FCFS, whatever process that come first, we execute them first. Now let's find out the waiting time for each processes. So let's just erase this out. And draw a column for the waiting time. So the waiting time for the first process is zero, because the first process came at 0th time and it didn't have to wait at all. It just executed however, like at whatever time it arrived, it just executed at that time. So the waiting time for the first process is 0 minus 0, like this burst time in the Gantt chart minus the arrival time here. So it will be 0. The waiting time for the first process is 0. Now it executed till 5 seconds, alright, but within that time the process P2 has already appeared in the queue. Has already appeared in the CPU. So, but we had to complete this whole process till 5, and then we just started we just started executing process P2. So it had to wait some amount of time, right? So 5 minus 2 is 3. So the waiting time for process P2 is 3 because it had to wait 3 seconds to execute 3 more seconds to after arriving at 2 seconds, it had to wait 3 more seconds to get executed. So 5 minus 2 is 3. So for P3, same way, 9 minus 4 is 5. It had to wait 5 seconds. And for P4, the waiting time is 12 minus 6, so 6. It had to wait 6 more seconds to get executed. Even though it arrived at 6th second, it had to wait 6 more seconds. It started executing the 12th second, the 12th second, yeah. So that's why it had to wait 6 more seconds longer to be executed in the CPU. So yeah, this is the waiting time. Usually in the books, in the main book that you read for operating system, the arrival time is not even there. It's just burst time, process. At that time, it's the easiest. If you have no arrival time, it means that all the processes came in this manner, in this sequence. So you just execute. You'll get the same Gantt chart, but in that case, the arrival time will be the waiting time will be different. How is it going to be? It's going to be like this. The waiting time for the first process is going to be 0. The waiting time for the second process is going to be 5. The waiting time for the third process is going to be 9. And the waiting time for the fourth process is going to be 12. right? Because all of them appear at the same moment. They what you call, they appear in this sequence, whatever the sequence that's given, and they'll just be executed in that sequence, and they would have the waiting time like this, since they have no arrival time. But in this case, when you have arrival time, you have to like subtract the arrival time from the visiting time. This is the visiting time and this is the finishing time. You can, like, while you're coding, like implementing this through code, you'll see that this is the visiting time, this is the finishing time, visiting time, finishing time, visiting time, finishing time, and so on. Alright, so that's about it for first come first serve. I hope you understood, and it's fairly easy, trust me. When you go to shortest job first, non-preemptive and preemptive, it's gonna look hell lot harder than this. So yeah, please don't forget to subscribe and give a thumbs up to this video, and good luck. Algorithm, which is one of the two algorithms of the shortest job first format. Now, non-preemptive is easier than the preemptive shortest job first algorithm, because this is just the shortest job first algorithm, which does not require remaining time. I mean, it executes the whole process as it is. It's kind of similar to first come first serve, but not really. You'll see that in first come first serve, what happens is it totally ignores the burst time of the smaller processes. But in this case, it does take into account that that will give priority to the smaller burst time processes first. So the process arrival time and burst time are given. Let's draw the Gantt chart for this, and then we can find out the waiting time and the average waiting time. Alright, so for this, the first process that comes is at the 0th second. So P1 comes first. So P1 will be executed fully. Okay, because as a non-preemptive, we do not like take into account within that time some smaller processes come, and we're gonna take this and store it in some array and then complete those processes first. No, it's not like that. We don't preempt the process. We just do the process fully. We don't do it incompletely or anything. Alright, so it will be executed for 5 seconds, and within 5 seconds, all only P2 and P3 has arrived. This is the arrival time of P1 0, the arrival time of P2 2, and P3 is 4. Within 5 seconds, P2 and P3 has already arrived in the CPU. So we can choose from P2 and P3 the shortest job first. From P2 and P3, which is the shortest job? P3, obviously. So we're going to choose P3 now. So P3, and 5 plus 2 is 7. Alright, so now within 7 seconds, see, all the processes have arrived. P4 and P5 has also arrived within 7 seconds, because the arrival time of this is 7, arrival time of this is 6. So obviously within this time, while the CPU was executing P3, these two processes have arrived. Alright, so now we can take into account these two processes as well. Well, P1 has completed, P3 has completed, so we don't need to worry about these anymore. These are all done. Only the processes that are left are P2, P4, and P5. So which is the shortest job among P2, P4, and P5? It's P5, obviously. So we execute P5, and 7 plus 1 is 8. Right, so P5 is done. Now the shortest job among these two are P2 and P4. Among these two, P2 and P4 are P2. So first we execute P2. So 8 plus 3 is 8, 9, 10, 11, 11. And then we execute P4. 15. Alright, so this part is not needed. It's unnecessary. So we have got the Gantt chart sequence for the non-preemptive shortest job first algorithm for this amount, for the information provided. Now let's, these are all done. Now let's find out the waiting time. Alright, as usual, waiting time is always the visiting time minus the arrival time. The visiting time is this for P1, the visiting time is this, for P3 the visiting time is this, for P5 the visiting time is this, P2 this one, P4 and this one. Alright, so for P1 the arrival time was 0 and the visiting time is 0. So 0 minus 0, waiting time is 0. For P3 the arrival time was 4 and the visiting time is 5. So 5 minus 4 is 1. Sorry. Alright. And for P5, the arrival time was 7. The visiting time is 7. So 7 minus 7 is 0. So P5 did not have to wait at all. For P2, the visiting time is 8. The arrival time is 2. So 8 minus 2 is 6. For P4, finally, the visiting time is 11 and the arrival time is 6. So 11 minus 6 is 5. Alright, so this is the waiting time, and you can find the average waiting time. Just 0 plus 6 plus 1 plus 5 plus 0 divided by 5 will give you the average waiting time. Now, what is this column that we have written down here? It's the turnaround time. Now, like I said in the previous tutorial, which I forgot to show, and I'm sorry about that, the turnaround time is basically the waiting time plus the burst time. So the turnaround time for P1 would be 5, turnaround time for P2 will be 9, for P3 would be 3, P4 will be 9, and P5 will be 1. So these are the respective turnaround time for the respective processes, and that's about it for non-preemptive shortest job first. But if you would like, I can show you another example. Let's look at this example. P1, shortest job first, CPU scheduling. And like I said, it is the harder part, the second hardest of all the CPU scheduling algorithms among the 5 CPU scheduling algorithms. So as usual, we'll always be looking for the shortest burst time as usual, but we preempt a process when we come across a shorter process while we are executing the current process. Yeah, that sounds really confusing, but it will get easier once you watch the tutorial. Alright, so we have all these processes here, and now, well, this looks like a really big table. Well, I'm starting out with the hard example, because if you understand the hard example, trust me, you can solve any problem that you come across for non-preemptive scheduling, because it covers every sort of problems that you might come across when you first do the tracing of the algorithm. So first off, we have the, as you can notice, there are no arrival time that starts with 0. The first process that comes is at the the 2 seconds. At 2 seconds arrival time, the processes start coming, and from then on, the processes start coming as 4, 3, 4, 5, 8. So within that time, from 0 to 2 seconds, the CPU stays idle. It does not do any sort of work at this time. It starts working from the process from the second from 2 seconds. It starts its actual work. So as you can see, in 2 seconds, 2 processes arrive at the same time, P3 and P5. So we select P3 because the burst time of it is it's lesser than P5. So when you have 2 processes that have the same arrival time, you count the burst time. You take the burst time into account, and when you have the same processes which have the same burst time, then you take the arrival time into account. So yeah, we take since it's shortest job first, we take the shortest burst time first, so P3. So we start executing. Let's start executing it like slowly. We're not gonna just write 2 plus 7 as 9. We're not gonna write 9 here. We just execute it slowly. Just slowly till 3 seconds it's executing. The CPU is executing P3. Now within 3 seconds, another process comes, which is P7. Now P7 is like shorter, like the burst time is lesser than P3. P3 you have already executed 1 second, so P3 has, this is the remaining time para. We just gonna write the remaining times here because while we are shorter than it in the meantime. So since we have executed 1 unit of 1 second of P3, so the remaining time is 6 seconds. And for this, the remaining the time is 5. Now, since 5 is lesser than 6, we execute P7. So P7, the main criteria is we're always looking for the shortest job first, the shortest burst time first. So P7 is shorter, so we execute P7, but also we're executing it slowly. So let's execute it till 4 seconds. Okay, like let's just execute 1 unit of it. Now within 4 seconds, another process comes, which is like the burst time is 3. It's P4. Well, this is shorter. Let's write the remaining time first. So we have 6 P3, P4 and P7 in our arsenal within this 4 seconds, and also P5, but P5 is too big, so we're not taking that into account. Within 4 seconds, the process that have arrived in the CPU are P3, P4, P5 and P7. Alright. And P6. So we have 5 processes. Now within this 4, 2, 8, 3, 6. All of the within these 5 processes, the shortest one is P6. So now we start executing P6 first. P6. Right, so P6 we again executed. Let's execute 1 unit again. Just do it slowly. It's fine if you're writing it twice. Now the remaining time is 1 and 4, 1, 8, 3, 6. 5 second. We have executed 5 second, and another process has arrived, which is P2, and the burst time of it is 1. But since we're executing P6 and the remaining time for P6 is just 1 second, so let's just execute it and finish it. I mean, we can do this, but then it's better if we just take this, because P6 we're already executing, and we're comparing P6 with P2 because P2 is smaller. We're supposed to take P2, but then we should be taking P6 because it has 1 second left, and since we're already executing it in the CPU, instead of switching to another process, and that context switching, when you're switching to another process, that's like context switching has overhead, like it's at that time when the CPU switches from one process to another, there is a little bit of time lost within at that time the other process stays idle and stuff. So the context switching time is purely overhead. So instead of switching to another process, let's just execute the one we have, and since the time is the same, I mean it's still it's still the shorter job than all the others. We're just gonna execute P6 and finish it fully. So we execute it till 6, so 4 to 6. Alright, so P6 is done, so it will be 0. P6 is totally done, we don't need to execute it anymore. Now, till 6 seconds, we have all these processes, okay? P2, P3, P4, P5, and P7. P6 is done. So let's just execute the shortest job first, which is P2 now. So P2, and it's just 7 seconds. Alright, so P2 is done fully. P2 is now out of the way. P6 is also out of the way. Now we count P7, P5, P4, P3, and P1 didn't arrive yet because it arrives at 8th second. The shortest job first, which is 4, 8, 3, among 6, 3, 8, and 4. So now we're going to take P4 because P4 is the shortest job at the moment. Okay, so P4 we executed till 8 seconds. P4, and the remaining time is 2. Now within 8 seconds, P1 has arrived in the CPU, and P1 is shorter than P4 because the burst time for P4 is 2, burst time for P1 is 1. So we are going to execute P1 this time. So 9. Alright, so P1 is done. This is the remaining time is 0. P1 is fully done. Now the shortest job is among 6, 2, 8, and 4. The shortest job is P4 again, so we select P4. Now we complete it fully. We're not going to do 1 unit and check again because we know that 6 is of course bigger and 4 is obviously bigger, 8 is definitely bigger. So let's just finish it fully. So 9, 10, 11. Right? So the remaining time for this is 0 now. Okay, so now the jobs that are remaining are 4 second, 8 second, and 6 seconds. So P4 is done. So P3, P5, and P7 are left. So now we execute P7 because P7 is shorter. It's just 4 seconds, is 8 seconds, is 6 seconds. So we are going to be executing it fully because obviously 4 seconds is shorter. The burst time of P7 is shorter than all of it. And we don't need to switch to another process in the meantime, so obviously it's going to be 15. We're going to execute it fully, and within that time also no other processes are arriving, so we don't need to be like careful. Okay, we just execute 1 unit, let's see if another shorter process arrived. No, nothing's arriving. We have already all the processes in our arsenal at the moment, so we're just going to be executing the processes fully as it is. The shortest job of course first. And then after that, P7 is done. So we have P3 and P5 left. P3 is 6 seconds and P5 is 8 seconds. Let's execute it fully. So P3 is 15 plus 6 is 21. And then P5 is 21 plus 8 is 29. Now these kind of maths, you have to check the answer, right? Like if your answer is correct or not. And since there's also an idle time, you might be like, okay, maybe I'm just kind of confused about my answer. What you would do is first find the sum of the burst time. All right, the sum of the burst time is 7, 8, 9. 9 plus 3 is 12. 12, 13, 14. 14 plus 5 is 19. 19 plus 8 is 27. Right, so the sum of the burst time is the sum BT equals to 27. Right, and now what you have got is 0 to 29. Well, your answer is still correct because the CPU was idle for the first 2 seconds. So you don't need to take into account the 2 seconds, the idle time of the CPU. So you just, like the total time for this will be 29 minus 2, which is 27. So yeah, your answer is correct. The answer for you're supposed to get the total burst time here in this Gantt chart, in every Gantt chart actually, not just this Gantt chart. In every Gantt chart, the way you can check your answer is if the sum of the burst time is equal to the times you're getting in the Gantt chart in this axis, in this x-axis or whatever. Right, so yeah, that's about it for non-preemptive, the preemptive scheduling algorithm. What we basically do is we just preempt the process when we preempt the current process if we get a smaller process within that arrival time. And we have to find the waiting time, of course. Let's start finding the waiting time. Alright, so for P3, okay, so this waiting time is going to be tough to find out because as you can see, P3 has appeared here once, it has appeared here once, right? So we have to take into account all the waiting times then. So for let's start with P1 first, okay? Let's just go sequentially. Okay, so P1's arrival time is 8 and its visiting time is 8. So 8 minus 8 is 0. And since it has just appeared once, P1 has just appeared once. So we don't need to find the other P1s here. It's just appeared once here, so it will be 0. Let's go with P2. P2 has appeared also once. So this is done. P1, let's just color coded so that's easier for us to understand. Alright, so P2 has also appeared once and the burst time, the visiting time of P2 is 6. Remember, the first thing is visiting time, the second thing is the finishing time. So it's always visiting time minus arrival time. So P2's visiting time is 6 and its arrival time is 5. So 6 minus 5 is 1. Alright, and now for P3, let's go with P3. P3 has appeared 1, 2, and yeah, that's it. P3 has appeared just, sorry, not this. Can't even understand my own handwriting. Alright, so P3 has appeared once here and once here. Alright, so let's see, the visiting time for this is 2, so 2 minus 2 is 0. So that's fine. The waiting time for the first P3 is fine. Now what we do is the second time that P3 has arrived, we just subtract the visiting time we just subtract the finishing time of the first occurrence of P3 minus the visiting time of the second or the next occurrence of P3. Alright, that happens with all the cases. Okay, see, you've seen that once the process has appeared here, it has also appeared here. Like P7 has also appeared here once and here once. Same rule goes for all the processes, whichever has appeared once or more than once. Alright, so first we get visiting time minus arrival time, which is 2 minus 2, and then we get visiting time minus finishing time. Alright, so visiting time minus finishing time is 15 minus 3. 0 plus 15 minus 3, so which is 12. Right, so now let's color code the next one. Okay, P3 is done. P4, let's go for P4. So we have P4 here, and that's it. P4 has appeared just twice. Right, so visiting time minus arrival time. So 7 minus 4 is 3. 3 plus we have the finishing time here and the visiting time here. visiting time here and finishing time here. The second occurrence is visiting time minus the first occurrence is finishing time. So 9 minus 8, which is 1. So we get 4. Alright, P4 is done. Now let's go for P5. So let's select, it's this color. Okay, for P5, P5 has appeared just once here and nowhere else, right? So P5, the visiting time is 21 and the arrival time is 2. So 21 minus 2. 21 minus 2. So it's 19. Alright? 19. Okay? And now for P6. P6 has also appeared just once. P6 twice here, but then they're appearing at the same, like, you can just write this as P6 fully for this whole box. Because it didn't context switch. I mean, all this process they switched. I mean, the P3, then it executed P7. It switched from one process to another, but this one they didn't switch. They were just executing the same process. So we just take into account this time here. So 4 visiting time minus arrival time, which is 4 minus 4 is 0. So the waiting time is 0. For P7, it appeared, let's change the color first. P7 has appeared here once and here once. Alright, so P7, 3 minus 3 is 0. So 0 plus this finishing time and this arrival time. So 11 minus 4, we get 7. So the waiting time is 7. Alright, so these are the answers for the waiting time: 0, 1, 12, 4, 19 and 7. So yeah, that's about it for today's tutorial, and I hope you understood everything. This is the hardest problem that you can ever get for non-preemptive. Well, hardest as in, of course, computers can calculate more bigger numbers. We're just doing it with smaller numbers, and this is the hardest problem you can get in an exam because it covers everything. It covers the idle time thingy, the idle time calculation, what you would do when a process arrives like not at 0 second, it arrives at later than 0 second. Then you just execute this, you just indicate this as the idle time, and then you start continuing the Gantt chart from there on. And then you have the examples of how to find the waiting time, because when there's a process appearing twice, like P3 has appeared twice or thrice or any, like more than once, whenever it has appeared more than once, you apply that rule. Like you just, first you do the same that you always do, like talking about the fourth CPU scheduling algorithm, which is priority scheduling, and this is another easy algorithm, just like the first come first serve algorithm. The main as you can see that there is no arrival time given here. Even in the first come first serve algorithm, that time there wasn't supposed to be an arrival time, but you can give an arrival time. It doesn't really matter. Whenever there is no arrival time given, it usually means that AT equals to 0, that is arrival time equals to 0, which means that all these processes, you see, all of them have arrived at the same time. So since they've arrived at the same time, the only thing that we care about is the priority that's given, and the lower the priority, the higher the lower the number, the higher is the priority. So based on the priority, we execute that process first. So since the priority of this is 1, we start executing P2 first. Alright, so 0, 1. So we execute P2 first, since the burst time of P2 is 1. Then we execute the second priority process, which is P5. So P5, we execute it. So 1 plus 5 is 6. Then the third one is P1. So let's execute P1. It's a really big process. So 6 plus 10 is 16. Fourthly, we execute P3. So the burst time is 2, so 18. And P4 is the last process that we execute. So P4, the burst time is 1, so 19. Alright, so this is done. This is the Gantt chart that we get. Now let's find the waiting time. The waiting time for P1 is, since the arrival time is 0 and the visiting time is 6, so 6 minus 0 is 6. So the waiting time of P1 is 6. P2, the visiting time is 0, the arrival time is also 0, so 0 minus 0 is 0. Alright, so P3, for P3 the visiting time is 16, the arrival time is 0, so 16 minus 0 is 16. P4, the waiting time is 18, and the arrival time is 0, so 18 is the waiting time. And P5, the visiting time is 1 and the arrival time is 0, so 1 minus 0 is 1. Alright, so this is the waiting time, and you can find the average waiting time is just the sum of the waiting time divided by the number of processes. Alright, so that's about it for priority scheduling. This was another really easy algorithm